there were no such thing as distance in the universe, why would we be so far apart? The reason we even ask this question is that space is not as simple as we once imagined. Space and time are actually a single structure. In classical physics, time flows at a constant and independent rate for all objects. But that perspective is not sufficient to explain the universe. According to general relativity, space-time is not flat. It bends in the presence of massive objects. In other words, space-time is a four-dimensional structure that can be curved by mass, and everything in the universe exists within it. According to Albert Einstein, gravity is not a force. It is the result of mass bending space-time. Objects do not pull on each other. They move along the curves of bent space-time. Anything with mass warps space-time. You can think of space as where you are and time as when you are. This perspective takes us far from the physics we are used to. It raises an intriguing question. If space-time can bend, could it tear and form a tunnel? We can imagine space as a fabric into which all objects in the universe are embedded. This analogy helps us visualize curvature. Massive objects such as stars, planets, and black holes cause this fabric to curve inward, much like placing a heavy ball on a stretched sheet makes it sag. Einstein's view of gravity fundamentally changed physics. He argued that gravity is not a force, but the curvature of space-time. When physicists examined Einstein's equations more closely, they discovered that these equations allowed for some strange, yet mathematically valid solutions. One of those solutions suggested that two distant points in space-time could be connected by a shortcut that would otherwise be impossible. Imagine you need to travel from one end of a city to the other. Normally, you would navigate street by street, taking a long route. But imagine there is a subway tunnel underground that takes you directly to your destination without worrying about the surface distance. The idea of a wormhole is similar. Traveling through normal space is like walking the streets. A wormhole would be a theoretical shortcut through space-time itself. In physics, this type of shortcut is called a wormhole. The idea did not arise from pure speculation, but because mathematics indicated it might be possible. That is why wormholes are more unsettling than science fiction. They challenge our concept of distance. If two points can truly be connected in this way, then distance may not be as absolute as we assume. If space-time can bend, then in theory, two distant points could be brought closer together. However, there is an important distinction. Bending means following a path within space. But what if the distance itself changes? At that point, our usual analogies begin to fail. A subway tunnel is still a path built within space. A wormhole is more radical. It does not create a path within space, it manipulates distance itself. Consider a sheet of paper with a dot at each end. If you fold the paper in half, those two distant dots suddenly touch. A wormhole is the space-time equivalent of that folding idea. It would be a theoretical tunnel that connects two distant points by shortening space-time itself. But what exactly is a wormhole? Wormholes are structures that are mathematically allowed within general relativity. In theory, they could exist. However, we do not know how they would form, and none have ever been observed. The term hole is only an analogy. Nothing is literally torn open. A wormhole is not an empty cavity in space, but rather a passage connecting two points. Space-time does not rip apart. Instead, distance behaves differently from what we are used to. Could a wormhole be kept open? In theory, maintaining such a structure would require an unusual form of energy. We do not know how to produce energy at that scale. Although Einstein's equations allow wormholes, the problem is stability. These structures are extremely unstable and would collapse under the slightest disturbance. They exist mathematically, but they do not remain open in practice. Physics does not say they are impossible. It says we cannot build them, at least not yet. The main issue is preventing collapse. In theory, the only thing that could stabilize a wormhole is negative energy. This type of energy would push space-time outward rather than inward. It appears rarely in nature, and we have no idea how to generate the required amount. So wormholes cannot remain open because we lack the necessary energy. Is there any hope? Possibly. Physics does not completely reject the idea. We do not yet know how to obtain the energy needed to stabilize them. But this would not be the first time something existed only in mathematics before being observed. Black holes were once purely theoretical solutions. Gravitational waves were predictions for a century before technology finally detected them. The same could one day be true for wormholes. Through new forms of energy, new theories of physics we have not yet discovered. Still, this is a possibility, not a guarantee. Wormholes may seem like fantasy today, but that does not mean they are impossible. Physics does not forbid them. We simply do not yet know how they could be realized. Perhaps the most fascinating question is not whether wormholes exist, but whether the universe is far stranger than our imagination allows.